In section 8, we turn to the essence of the cross-lagged analysis. That is, we look at two processes jointly, suicidal ideation and substance abuse, and look at how they relate to each other. On slide 67, you see then the response patterns again, and this time for both variables. So we have, with 8 time points, we have 16 different variables to look at. And the pattern of zeros for both sets of variables across all time points is 104, which is less than the people in the zero pattern for either one of the processes, as only 14% of the total sample. Although if you take into account the percentage of zeros and or missing, we have about 29%. But 104 is a pattern that we'd like to fit well as we go on. Now, so we're doing a bivariate analysis, and here I'm showing it in the new way using the y-hat approach. So you have the process for suicidal ideation and the process for substance use here. Correlated random intercept variables, and then you have these residuals across that have a dynamic interaction across time, and then the cross lags between those residuals with a contemporaneous residual correlation across the two processes. Now, the old style of describing the model is shown here using the WSMV estimator for the RI-AR1 model. When I say RI-AR1, I mean that you have autoregressive order 1 for both processes, and that's the model that we typically call RI-CLPM. So the variables are categorical, estimated WSMV, we use parameterization theta, and we have the two random intercept factors here, and then we define these within factors for each of the variables, for both Y and for Z, suicidal ideation and substance abuse. And we fix the residual variances at 0, in line with the old style of doing things. And the new thing is that we fix the variances of these within factors to 1. But then we have the regular first order autoregressive relationships here for each of the two variables, and the cross lags here. And then the contemporaneous residual covariances there. That's the old style, but corresponding to the plot I just showed you, here's a new style. On the left for WSMV and on the right for base. So for WSMV, you do the same definition of the random intercepts, but then you go straight to talk about the residuals. Here is the pairwise on regressions for the AR1 for Y and for Z. And then you have the cross lags Y on Z, Z on Y, and the contemporaneous residual covariances. And in the output, we like to look at the standardized solution. That's the one I prefer to show, given that the metric is arbitrary here with categorical outcomes. We want to look at the residual, and to get information about the response pattern fit and bivariate table fit, we need to add Tec10. For base, you change estimator to base, and typically for bivariate models you want to have at least 2,000 iteration, maybe I use 5,000 quite a lot, and a little bit of thinning, that is skipping the reporting of some of every, only reporting every 10th iteration to get values in the MC-MC process that are less correlated. Processes equal 8 to make it go faster. That can be used also for WSMV. And other than that, the model is the same as for WSMV on the left. And the only new thing we do is we ask for Tec8 here in base, so we can study the convergence of the process in a more hands-on way and not leave it to Mplus to decide. looking for that PSR to go down to 1 for a long stretch of iterations. And if you're unfamiliar with Bayes, again, I mentioned the short course topics that we have on our Mplus website that you can go to for an introduction. So here are the bivariate analysis results then for suicidal ideation and substance abuse. And I should mention that for all these models that I look at, the outputs are posted on the website of the talk. So for 8 time points and 2 variables, we have 16 times 16 minus 1 divided by 220 bivariate tables. So we have 480 cells that can contribute to misfit for the bivariate tables. 5% of that would be 24, so we have the rule of thumb then that we want to have less than 24 ill-fitting residuals. So again, we report it in terms of different models, number of parameters, PPP for Bayes, chi-square for WSMV, and then here we have the TEC10 output, number of significant residuals for the response patterns and for the bivariate tables, and then my comments on quality of fit. The AR2 model, that is what's customarily called the CLPM model, with the lag 2 is what we consider here. We decided from the univariate analysis, the analysis of each of the 2 processes separately, that we needed a lag 2 model. The AR1 model would not be sufficient. And that has a fairly decent PPP value using Bayes, and actually a good, perfect fit to the 20 most frequent response patterns, and a very acceptable number of significant bivariate residuals. So good fit for that model. If you use WSMV, we get a little tougher judgment of fit in terms of chi-square, and here it's a matter of taste whether or not you think that's fitting well enough. The p-value is less than 1%, but at least it's not 0. And looking at the residuals, we have 0 ill-fitting response patterns, that's good, and we have only 1 bivariate. I call that a marginal fit, mostly due to the low p-value here. But it's approximation that seems to be reasonable. And then we have the ARMA model, and whenever we have MA, moving average component, we use WSMV. So for the same number of parameters as the AR2, we get a very well-fitting model, but again, we have chi-square less than the number of degrees of freedom, so to me it seems like we're using more parameters than are necessary. Adding a random intercept to the model, we have found that having AR1 for the first process and AR2 for the second works well. So this is then getting a good fit for Bayes and a reasonable fit for WSMV as well. Except for WSMV, we have a negative random intercept variance for Z being substance abuse. So one would have to get rid of that to modify the model and get on. But instead we're going to continue looking at the models of primary interest here, namely the RI models, RI-AR and RI-ARMA, where we do this separation of within and between individual variation and covariation. So we pick an RI-AR12 model, so an AR1 process for suicide and an AR2 process for substance abuse. So we have a very good fit here, and we have a good fit also for the WSMV version of that, except we get an NPD, non-positive definite solution, and in this case that's not a negative random intercept variance, but it's actually a correlation between the residuals, the contemporaneous correlations in one case is greater than 1. So it's not perfect for the WSMV version of the model, but Bayes does okay. And then we have RI-ARMA, and that gives a good fit, but once again it seems to be over-parameterized for these data. It's a simple model where we fix the random intercept variance to 0 for suicidal ideation based on the separate analysis of that process. Now one can have many other models as well. One can mix models for the two processes. One can have an AR model for one process and RI-AR model for the other process, for instance. But that doesn't give any clearly better model than what I'm showing you here. I should mention also that for the RI-AR12 model here, the random intercept variances are substantial. That is, the variance estimate is a lot larger than its standard error. Now one can also ask, well, what if we start trying to free the first residual variances, as we discussed earlier in the technical section? There is a possibility to identify at least one of the residual variances different from the fixed value of 1. Well, I did that for these models, for instance for the RI-AR12 model, and it doesn't buy you much. First of all, the residual variances are not significantly different from the fixed value of 1 that we're using here, and the standard errors for some cross-lagged effects go up to the point of making them insignificant. So that doesn't help. Moving to slide 72 then, I want to show you how one can do testing of time invariance across these different models using model test. So that's a walled chi-square test in the Bayesian context. And here we apply it to the RI-AR12 model, the RI-CLPM 12 model. So we run a non-invariant model, but then do the invariance testing of cross-lagged effects and covariances. I choose the cross-lagged effects and covariances only for testing because I'm interested in the bivariate, the interaction between the two processes. You could also test invariance of the autoregressive coefficient across time for each process, but maybe that's of less interest. All of that can, if it's true, if it holds, can stabilize the estimation and bring smaller standard errors. So here we do it in the Bayesian context, and here I have asked for at least 5,000 iterations, thinning of 10, processes equal 8, and specify it with the hat approach. So here is the autoregressive for y of order 1, and for z we do it of order 1 and order 2, so the AR12 as we call it. And then we have the cross-lagged effects and the contemporaneous covariances between the residuals. And we label them, and then we test in model test whether, for instance, D3 is equal to D2, if the difference is 0. So that's saying that the cross-lagged effect Y2 on Z1 is the same as the cross-lagged effect Y3 on Z2, etc. So here are the cross-lagged effects for Y, and then the cross-lagged effects for Z using the E label, and then you have the covariances here. So this is how you would lay it out. Now, I did this time invariance testing with model test for both WSMV and for Bayes. So this is a little complex of a table to read, but let's go through it slowly. So consider the first model, the AR2 model or CLPM2 model, and let's test the time invariance of the cross-lags separately from cross-lags and residual covariances. So for the cross-lags then, we get 12 degrees of freedom, we impose 12 restrictions, and get a chi-square value that's not really strongly significant. Now you add covariances to that, then you get a pretty well-fitting model, testing that. And if you impose both of those, so you can't really reject invariance of cross-lags and covariances for WSMV for this model. And if you impose both invariances, you get a model that's like this. A little bit ill-fitting, but not too bad. Certainly not bad in terms of the significant residuals for the patterns and the bivariates. If you do the same testing for base, you get you can't reject the cross-lag, that cross-lag effects are invariant, nor can you reject that both of them are invariant, the cross-lags and the covariances. And here's the PPP value for the model where you impose them. So these two runs here, first two rows, are in a run where you do not impose any invariance. So you do model test here. But once you've done model test, you can impose the invariances if the test came out that way, and that's a separate run. So we can't reject invariance for this model. And then you can go through and do the same thing for the RI-AR12 model, and I won't go through that here now. I'm just saying that both being invariant here gives a poor fit, so we don't take a look at the patterns and the bivariates here. It's just a poor fit based on the testing of invariance. So we reject it in that case. Going to the next slide then, 74, let's look at our model RI-AR12, which is the one I'm favoring here. And you can't really reject the cross-lags being invariant, not very strongly at least. Certainly not when you test them together like this. And imposing both being invariant, well, for WSMV, that causes a negative variance for the random intercept variance for substance abuse. But for base, what happens there? Well, you can't reject invariance here, certainly. And you have a well-fitting model in terms of PPP and in terms of the residuals from Tech 10. For RI-ARMA, you have not a clear rejection, but when you impose both being invariant, you get a negative variance for IZ, for the substance abuse random intercept variance. So if you then summarize this and look at the estimated cross-lagged effects, suicidal ideation and substance abuse show differing patterns of cross-lagged effects depending on the model and how you estimate. So we have 3 columns here. We're going to make an important point here that WSMV should perhaps always be complemented with bootstrapping. And I'll tell you why in a second. And then over here we have the base estimator. So we look at the different models that we considered, some of them being invariant, imposing invariance across time, and some of them not imposing that. And then we look at the cross-lag of Y regressed on Z and Z regressed on Y. Now for that invariant model, the number of significant cross-lags is 1 for each. There is only 1 of each, and that's significant. As we will see, however, that's a very small effect that's of no interest from a practical perspective. You get the same result with bootstrapping and the same result with base. But look at the other model here, RI-AR12. Here you get 7 this is not invariant, not an invariant model. You get 7 significant positive effect for y on z and 1 for z on y using WSMV. But if you use Bootstrapping 500, it drops down to only 5 positive. And if you go base, then you have only 1 positive significant effect. So here's a situation where WSMV, I'm going to show you simulations later on, has a tendency in this model for this sample size and for this prevalence to give underestimated standard errors. And the standard errors are better estimated by bootstrapping, but bootstrapping is not as good as base. Bootstrapping is like 500 draws of a distribution of parameters, whereas base does 5,000 draws. The true variation of WSMV is larger than base. True parameter variation is larger than base. But the standard errors are underestimated when you don't do bootstrapping, which tends to make cross-slide effects significant, look significant when they're not. If you then move down to RI-AR12, you can see that here you have 3, that's not the invariant model, 3 significant effects for y on z hat, and z hat on y is only 1. But when you go to WSMV, it goes down to 2 and 1, and when you go to base, it goes down to 1 and 0. So base is the more trustworthy approach here. Now for RI-ARMA, we can only do WSMV, and here we do it with no random intercept variance for suicidal ideation, and we have the invariant model here, and here we have nothing for base to compare to, so we have to rely on WSMV, and we get 1 significant effect for both. We're going to talk more about the size of the effects in a second. Now you also have to recognize that when you do bootstrapping with WSMV for variables that have low prevalence, proportion 0.15 to 0.20, there will be unsuccessful bootstrap draws. So for the 5 models here listed, except for M model 3 where we don't do WSMV because it wasn't invariant for WSMV. Here for 500 draws, the number of successful draws were 459, 405, only 93, 485, 470. And we have a paper on that. It's a technical paper. It's listed at the end on bootstrapping issues, bootstrapping failures that you can study. Now, if you focus on one estimate here, y7 on z6, and look at the posterior distribution of the base estimate for one of the model, the non-invariant model, you can see that the base posterior distribution has very long tails. So if you look at this, the midpoint here, the estimate around 0.16, 0.15 maybe, and it goes up to 0.32. But given that it has such long tails, the lower limit of the confidence interval goes down into a negative value. So this would be deemed insignificant. But you may consider the fact that most of the distribution is in the positive area, is on the right side of 0. So the mass of the distribution shows significance. It's just that we don't have enough of a sample in this case to move in the tails, make it a more peaked distribution. The bootstrap distribution has a similar shape. You can get that by plot 3, as I say here. So the bootstrap distribution gets closer to the what the Bayesian analysis gives. So here are the conclusions on slide 77. Using Bayes for AR2 for the CLPM2 model and Bootstrap WSMV RI ARMA with time-invariant cross-lags and residual covariances, that shows significant but very small cross-lagged effects. The effects are around 0.05 in a standardized fashion metric, so that's of no practical interest. Using Bayes with time-invariant cross-lags and residual covariances, neither RI-AR12 or the RI-AR12, RI-CLPM 12, show significant cross-lagged effects at all. And you can ask then, is it perhaps due to lack of power because we have small sample size for low prevalence variables? When I say small n, it's 737, so it may not be considered small, but relative to the prevalence, it is small. And we would see how big of a sample you really should have in this case. Or is there a lack of power in rejecting invariance? Maybe we should not impose invariance. We're going to take a look at that also. And perhaps there is invariance across part of the time scale. We're going to see that there is a difference between early time points and later time points. So here you may ask at the end, where did the correlations between the two processes go that we looked at early on? Well, little of it went to the cross-lagged effects, and where they went is to the intercept being correlated and to the contemporaneous residual correlations. Finally then, on slide 78, we could bring in covariates here as well, and in this data set we have covariates such as gender, race, and an indicator of poverty. But you find here no effect of those variables on IY, the random intercept for suicidal ideation. Only the last 5 time points, if you analyze them separately, only in that case does female have a positive effect that is increasing the random intercept for suicidal ideation and therefore increasing the probability of suicidal ideation responses. So female has a positive effect and black has a negative effect. Female and black have a negative effect on IZ, however, even in the t equals 8 case. That is an effect on the substance abuse.